Hello everyone, and welcome to Comprehensive Rocket Science, the channel dedicated to providing quality educational content on rocket and spacecraft propulsion and design. My name is Rob Roundtree. So today's video was initially going to be continuing our series on an introduction to launch vehicles. However, with that being said, I ended up changing it up because the vehicle was longer than intended, so this video is going to be all about orbits. And keep in mind, this is still just introductory material, so we won't be going in a ton of depth right now, but this should give you a good overview. In our last video, I demonstrated mathematically that gravity is roughly the same in space when you're close to Earth, say 200 kilometers away or so, as it is on Earth. So one thing I wanted to note there before we get started, I had mentioned the ISS altitude was 200 kilometers. It's actually more like 400 kilometers and some change. It's 220 miles. I was misspeaking there. So at that altitude, at any low Earth orbit altitude, 200 kilometers, 400 kilometers, gravity is going to be about the same force that it is when you're just here on Earth. So how do you actually stay in space for a long period of time if gravity is the same? I mean, you're not escaping gravity, so wouldn't you just fall back down? Well, yes, you are constantly falling back down, is the answer to that. But the way you get around it is you're in orbit. And literally, when I say get around it, I mean you're actually having to go around the Earth. So here's the Earth here, and then here's the trajectory. Say you're, you've got your atmosphere up here, and here's your rocket. You're above the atmosphere, you're, say 200 kilometers above the Earth, and you're going to be, you're still going to be falling, and you're going to be falling at your standard rate where, gravity, right, is pulling you down at, 9.8 meters per second squared. So that doesn't change. The only thing that changes is this trajectory is actually includes you falling at 9.8 meters per second squared. You're going so fast sideways that as you fall, you're falling around the Earth. And you'll see, draw a picture of the Earth. What's happening is as you fall, you keep falling and falling and falling and falling and falling, and you never hit Earth. And in fact, in a perfectly in any orbit, you'll end up right back where you started. And in a perfectly circular orbit, you'll stay the same altitude over Earth for the duration of your fall. Now, so hopefully that makes sense. Just to clarify a little more, so any projectile you fire, right, be it an arrow, a missile, anything, you're going to have, it's obviously, it has some velocity, but it's also falling, and that's what causes it to, make sort of a parabolic trajectory where, you start maybe shooting it up, so you have, a little guy here with a bow and arrow, and he shoots his arrow. The arrow is going to go up, and then it comes back down because gravity is pulling it down. So you have the same thing with spacecraft, right? The only difference is you're going so fast that as you fly around Earth, you're actually, Earth is falling away beneath you, and you never actually touch Earth. That's all orbit is. And then another thing I wanted to cover here was, so you're in orbit, right? And this, you're going to experience less air resistance than you would, but air resistance doesn't totally go away, not 100%. So, here's the surface of the Earth, and you're, say the atmosphere looks something like this, and then, as you get higher, the atmosphere kind of thins out, and it thins out more, and, up here, there's essentially no atmosphere. But it doesn't actually completely go away, at least not when you're in low Earth orbit. It is negligible, so you may be hitting, 1/10,000th of as many air particles as you would on Earth. I'm making that number up. It could be something entirely different, but the way you think of it is you have your your density of air versus altitude, and as your altitude goes up, your density of air comes down exponentially. and actually it would intersect right here at sea level. There's a specific point. But the density of air is decreasing exponentially, but then when it gets down here, it kind of approaches an asymptote where, you know, it takes longer and longer for it to actually hit. And, you know, theoretically, even way out in space, there's a little bit of air. Now, obviously, it's completely negligible at that point. But, you know, and when you're in low Earth orbit, for our purposes, it's also negligible, but just know that spacecraft do experience a little bit of drag, so you're not actually able to stay in forever without firing your engines. But once you get past, you know, a couple hundred kilometers, it starts being really, really low, and you can stay in orbit for a long time without doing anything. And that's an issue actually with space debris. One thing we talked about in the last video was the fact that as you get higher in around the Earth, the gravity is actually weakening a little bit, right? Because your vehicle is further from Earth. You know, that was that relationship that we demonstrated where, let's see, force equals gravitational constant times mass of your rocket times mass of Earth divided by the distance between them squared. And, you know, as the distance goes up, obviously, the force, or, you know, the acceleration, which is just force divided by mass of your rocket, is going to go down, you know, squared. Because you're experiencing less acceleration higher up, you will actually be going slower, but because of, you know, it requires a lot of energy to get up there, you will actually, you know, it's always going to be more efficient to be at a lower orbit, basically. So, you know, we're going to talk later about how you will be going slower when you're higher up, but that doesn't have as much to do with actually the speed that you're required to get your rocket to. You actually initially have to get your rocket faster to get up into this higher orbit, but what it does mean is that you're going slower because you are having to fight Earth's gravitational potential. So, you know, gravity obviously is constantly affecting this problem, and as you go up, gravity is accelerating you downwards, so you're getting slower and slower as you get higher. But and then there's a relationship with just with physical mechanics for uniform circular motion that governs this, but we'll talk about that later. For now, just know that it's generally most efficient to have a low orbit. Now, of course, there are limitations there. Obviously, you don't want to be in the atmosphere or anything like that, but that is generally the case. Sorry, my writing is so terrible. Alright, so we talked about, you know, to stay in orbit, we need to be going really fast around the Earth. Well, okay, that's great, but how fast do we need to be going? What are we talking about here? The answer is really fast, and we can actually do calculations that will show us this. So this is just a basic high school physical mechanics, uniform circular motion. So we're going to assume here that your spacecraft is traveling in a circular orbit around Earth, so its altitude is the same at all points around Earth. And you know from just physical mechanics, like I said, high school level, that your radial acceleration, AR, your radial acceleration, is equal to your tangential velocity divided by the distance between your point of rotation and the edge of your circle. So yeah, AR equals VT squared over R. And this is only for uniform circular motion. Uniform circular motion. Like I said, my writing hopefully will improve eventually using this tool. So with this, so we know that our acceleration here, we actually know that, right? Because acceleration is equal to the gravity you're experiencing up here. AR equals gravity, we'll call it local, G local, because remember that your gravity you're experiencing up at orbit is actually going to be a little bit less than what you're experiencing on Earth. And if you're, if you're in a really high orbit, if you're way out, 10 times further than this, then you're going to be significantly, you're going to have significantly less gravity than you would on Earth. But for now, we'll assume, we're staying low Earth orbit. It's pretty close. Regardless, either way, your only acceleration your vehicle is experiencing, as long as you're not firing the engines, is going to be g local, just the force of gravity pulling you down. So we talked about in the last lecture that force, so your gravitational force exerted between two objects is equal to the gravitational constant times the mass of the first object times the mass of the second object divided by the distance between them squared. And we generalize this to say that using F equals ma, where m is m1, the mass of your rocket, we can say that a equals F over m1, and therefore a in this case is equal to g, which is what this is talking about, your gravitational force between two objects. So we know that g equals F over m1 g m2 over r squared, g m2 over r squared, where r is the distance between the center of Earth and your spacecraft. So we know that AR is equal to g local. This g here is g local. That's going to be the gravitational force felt between Earth and your spacecraft. And this would be in contrast to g naught, or GSSL for standard sea level, which is the gravity you experience on Earth, which is on the surface of Earth, that is, which is 9.81 meters per second squared. Alright, so next what we can do with this is say that g local, I'm going to use the red since this is all new stuff, g local, because the only acceleration we're experiencing is gravity, local gravity, AR equals g local, as I said here, we can say that AR equals g m2 over r squared, and we know that from our uniform circular motion problem, for circular orbit is equal to vt, which is your tangential velocity, the velocity you're experiencing in your orbit, over r. Now, to find the velocity you need to be going, which your velocity in orbit, you can simply pull vt out of this. So from that, vt equals times r, the square root of g m2 over r, and that is going to be our tangential velocity. And we'll do a quick little unit check here. You'll humor me. Square root of, let's see, g has some very complicated units that I don't remember. Let's see, meters cubed, kilograms, meters cubed over kilograms seconds squared. Meters cubed over kilograms seconds squared times m2, which is just going to be in kilograms, divided by r, which is going to be meters. And with that, you get to, let's see, meters squared over seconds squared, which obviously the square root is meters per second. So that checks. Alright. So that's our equation for how fast you need to be going in any given orbit. Now let's say you're orbiting the Earth at, I know we used 200 kilometers last time, but that's where I was thinking the ISS is. It's actually 400 kilometers, so we'll use that. So it's a little over 400. So 400 kilometers equals h. That's going to be our altitude. Sorry, my writing is terrible. R is the radius of the Earth, which is equal to, let's see, 6.371 kilometers. 6.371 kilometers, so 6,371,000 meters. And m2 which is m Earth, is going to be equal to 5.972 times 10 to the 24th kilograms. 5.972 times 10 to the 24th kilograms. So, and then you obviously have G as well, which is 6.674 times 10 to the negative 11th. 6.674 times 10 to the negative 11, and those units were meters cubed over kilograms seconds squared. God, that was terrible. Did I draw that? Alright, meters cubed over kilograms seconds squared. Now, we can just do this math here, and, you know, oops. I'm not actually going to do the math in front of you, but I'll just write it out. 6.674 times 10 to the negative 11th over m2 is going to be 5.972 times 10 to the 24th over, what is that? So your r, little r, equals r plus h, right? Your radius of the Earth plus your altitude, which you have 400 kilometers, which is 400,000 meters, so here you end up with 6,771,000 meters. Alright, and then I didn't need the units there because I didn't use them anywhere else. We already did the unit check and we know that the units are good. So, from this you get your VT, which equals 7,672 meters per second, which will convert quickly to, well, that's actually about what we expect, so 7.6 kilometers per second. 7.6 kilometers per second, and you know, if you want to do a unit conversion to miles per hour, you can. 7.6, I'll say 7,672 meters per second times 3,600 seconds per hour times what is it, 3.3 feet per meter times, you want to do miles per hour, 5,280 miles per, sorry, 5,280 feet per mile, or if you're using nautical miles, it'd be about, what is it, 6,076. So, anyway, you do the unit conversion, and you come up with 17,262 miles per hour. That's how fast you need to be going. And, you know, if you are a kilometer kind of person, that's, what is that, about, we'll call it 20, I'm not sure, 28,000 maybe kilometers per hour. So that's fast. Divided by 0.62. Yes, 27,800. You know, for reference, I mean, a bullet, you know, some bullets barely break the speed of sound, which is 700 miles per hour, so you're going, you know, roughly 20 times the speed of sound at sea level. You're going extremely fast is the answer. Now, it's important, I do want to note that, you know, all these calculations we do here are for uniform circular motion only, which means Earth and this mass are the only two things that are in the problem. There's no other masses, say for instance the moon or the sun, that could throw things off, and also the orbit has to be circular. You know, you can't have any elliptical orbits. That's obviously going to change everything. And in an elliptical orbit, when you're at high altitude, which is called your, or the highest altitude is called your apoapsis, you're going to be at your slowest point, and then when you're at your lowest altitude, your periapsis, you're going to be, you're going the fastest that you will. We'll talk about that a little more. Okay, so we calculated, you know, our speed here, 17,262 miles per hour. Yeah, you have to be going really fast to stay into orbit. But, you know, something that's worth noting is, all right, you see your relationship here, Vt equals the square root of g m2 over r. As r goes up, so your distance from the Earth goes up, your velocity is going to be going down. Well, how is that? I mean, to get higher, wouldn't you need to go faster? So shouldn't you need to be going faster to get to a higher altitude? And wouldn't, when you're in a higher orbit, you be going faster? I mean, that makes some sense, right? If you, to get into orbit, you need to go really fast. To get higher, you go faster. Why is it that, at a higher orbit, you're not actually going faster? Well, as I mentioned before, this involves fighting Earth's gravitational potential. So, we'll say, here's Earth, and here's your spacecraft. And we know that gravity is going to be constantly pulling us down. It's just a fact of life. Now, you're in orbit here, fat and happy, sitting at your 17,000 miles per hour, which feels like nothing, by the way, because you don't feel velocity, you just feel acceleration. So you're sitting there, happy in orbit, going around. You're in a circular orbit. You're at the same altitude above Earth, and all of a sudden you say, okay, I want to increase my altitude. Well, how do you do that? So what's going to happen is, this is a very visual thing, so work with me while I try to describe this. What'll happen is, what you do is, you go in the direction, so say, there are two things you can do here, basically. You can increase your speed in the direction you're traveling. So we're traveling in this speed, this is our v, let's do our little velocity vector there, and you can either accelerate in the direction of your velocity, or the opposite direction of your velocity. Obviously, there are other things you can do in a three-dimensional problem. We're going to keep this real simple. You can either go A in the direction of velocity, or A in the opposite direction of velocity. And let's say that we want to do acceleration in the direction of your velocity, A. What's that going to do? Obviously, it's going to make you go faster, because V and A have the same sign. And obviously, for constant acceleration, which spacecraft don't experience, but we can just sort of make an assumption here that is incorrect. Your velocity is going to be, this is your speed, not your velocity. Speed is going to be equal to your initial speed plus acceleration times the amount of time you're accelerating, delta t. So that's for constant acceleration. Like I said, our acceleration is not quite constant. That's okay. This doesn't need to be equal, but it's an approximation. So as you accelerate, yes, you will be going faster. But because of the way this works, you are only going faster at this, well, that's not totally true. So you're going faster, but the only place you're guaranteed to be going faster is this one point where you started. Everywhere else, what this is going to do is it's going to cause you to climb into a higher orbit. So you start out, here's the Earth, here's your orbit. You start out here, you have some initial velocity v0, and then you have your acceleration, which we'll just call A. And then we also have negative g, pulling us down. Negative g, all it's doing at this point is keeping us moving around the Earth, right? We're constantly accelerating inward, which just turns the vehicle. This A, the one that's traveling with our v0, is tangential acceleration. And tangential acceleration in orbital mechanics, I'll use purple for this, is going to speed us up right here, and then it's going to increase our altitude for all other points. And basically, what ends up happening is your orbit changes. Your orbit is going to get larger on the opposite side of where you burned, or where you had this acceleration. You turned on your rocket motors, and your orbit is going to hit back to the center point of where you applied that acceleration every time. So the only place your orbit is changing at every point, technically, besides the point where you initially gave the acceleration. The point where you gave the acceleration, you're going to come back to that point constantly. And this is how, this is obviously, my dotted circle, dotted purple line here is an ellipse. So this is how you get into an elliptical orbit. Sorry if this isn't totally clear. I'll, hopefully this is Earth. Hopefully try to make this a little more clear, but, we're working with what we got. So, now you're in an elliptical orbit, and in fact, this applies universally to orbits, where when you apply acceleration, you raise all parts of your orbit except where you apply acceleration. Now, when I say raise your orbit, you start at some, initial height, h0 here, and you end up, at your highest point, we'll call h1, say this is your apoapsis, which is your highest point of your orbit. You end up at a higher point, h1. Now, this applies, anywhere along here, anywhere along your orbit, your burn. What you're doing is basically pushing out the opposite end of your orbit. So, this is your periapsis here. Periapsis, the lowest point of your orbit. Up here is your apoapsis. Apoapsis. My writing and my spelling both suffer here. That's spelled correctly, I believe, but who knows. Burning here will push out your apoapsis and cause you to have a higher orbit for the majority of your orbit. Now, same thing down here. If you were to apply an additional acceleration, so we'll say it's a different acceleration vector, but it's the same level of acceleration, same amount of acceleration that you applied up here, then you can actually round out your orbit. You can get into a higher circular orbit. So that's generally how you're going to get into a higher circular orbit. Burn, along your circular orbit. That's going to raise your apoapsis, and then burn at your apoapsis to raise your periapsis and circularize your orbit, is what it's called. So, hopefully that covers, the effects of burning prograde and the direction of your velocity. Now, there's another option here, which is that you could burn in the opposite direction of your velocity. Burning in the opposite direction of your velocity, and this does basically, if you can understand this, which I understand, this might be harder to understand if you don't have a decent foundation in orbital mechanics, which, this is, by the way, very simple orbital mechanics, but this could be difficult to understand if you don't know it already. I would recommend, if you want to know more about orbital mechanics and also have a great time at the same time, Kerbal Space Program is an extremely great tool in learning orbital mechanics, and it's also a lot of fun. So that's a good game. It's called Kerbal Space Program. Anyway, and if you're nerdy enough to watch this, you're definitely nerdy enough to play that game. So, but it's good. It's all in fun. We're having fun here. So now say you're in another circular orbit here. That's not a very good circle, but let's say this is a circle, alright? Your altitude is the same, you have h, you're getting pulled down by g, all the same kind of stuff, right? If you were to if you were to burn retrograde, so this is called burning prograde, burning in the direction of your velocity, is called prograde. Burning in the opposite direction of your velocity is called burning retrograde. Now that is, if you understand this, then this is pretty intuitive. What it'll do, it's going to lower your orbit at all points except for where you burned. So it's going to do this. It lowers your orbit. And your orbit will be lower down here, and it'll come back up here. If you started with a circular orbit, then now your periapsis would be down here, periapsis, and your apoapsis would be where you burned. Apoapsis would be where you started the burn. And then same thing, to lower your orbit, you want to burn retrograde at your periapsis. And if you think I learned all this from some textbook or something, no, I learned this from Kerbal Space Program mainly. If you burn retrograde at your periapsis, you'll end up with I know this is not scale. Tell me about it. You'll end up with a circular orbit, right? The red, it'll say, is circular. Okay, so, yeah, that's what you do. Burn retrograde, reduces the size of your orbit. So the way you can think of this is when spacecraft want to go higher, they'll burn prograde, and that is in the direction of their velocity. That'll increase their orbit. If they do the same thing on the other side, they can increase or raise the other side of their orbit and get in a circular orbit. Same thing, burning retrograde. If you burn retrograde, you will decrease the size of your orbit on the other side of the Earth, and then if you do it again, when you reach your periapsis, you'll circularize your orbit, reduce the size over here. And you can keep applying this, right, until you get the effect you want. So, as you burn prograde, eventually you can raise your orbit, so you started at this orbit here. Eventually, you can raise your orbit so much that you end up escaping Earth. The escape. And that's something that we will talk about a lot later, but yeah, that is what can happen at one end of the spectrum. And then on the other end of the spectrum, if you were to burn retrograde, you can reduce your orbit in size until you crash into Earth. And that's how they generally will actually deorbit. Second stage is if they have enough fuel, they'll burn retrograde and put them over the Indian Ocean or something. There's usually exclusion zones for that in space launches, and the aircraft, or the second stage spacecraft, will burn up in the atmosphere over the ocean. And they achieve that by inserting an object into orbit, a spacecraft into orbit, right? And then when they get to the right point, burning retrograde, and that trajectory will take them to burn up in the atmosphere over the ocean. So basically, those are the two extremes of burning prograde and burning retrograde. Okay, so everything we've covered here is extremely rudimentary, but hopefully it gives you a decent idea of the basics, and we can move forward from there. Okay, so that does it for today's episode. We went over what orbit is, how fast you need to be going to get into orbit, and some very, very basic orbital mechanics, as well as burning prograde and burning retrograde and how that affects your orbit. So in the next videos, I'll be talking about staging and air launch versus ground launched vehicles, so I hope you'll join me for those. Be sure to like and subscribe if you're enjoying this content. See you next time.